Right. So I have released the results already now of your midterm exams. Have you seen your scores? Yeah, so how did you find the exam? Is it easy? Right. So before we begin our discussion today, let's do a recap of what we have covered last time. So can anyone recall or can anyone share what they can recall from our discussion during our previous lecture? Guys, any volunteers who can share what they can recall from our previous discussions? Yes, Mr. Karinungan, please proceed.
Ah, ang nare-recall ko po last time is the Gaussian elimination and the Jacobi po.
That's right, no? Okay, so thank you. Okay, so last time or previously we have covered the approaches no, for solving systems of linear equations, particularly in matrix form. So today we will have just a very short discussion on some further techniques that we can apply to solve for matrices. No, this is called the LU decomposition. To begin, we can demonstrate how this method differs from the Gaussian elimination. But first, we have to define that this method begins with the original matrix A, now which we've been solving using the Gaussian elimination, or in some texts, this is referred to as the naive Gauss elimination. The original matrix A can be expressed, no, or can be rewritten in the form of the following equation. Now, so if you have the original matrix A, this can be broken down into two sets of matrices in the form of a lower triangular matrix and an upper triangular matrix. So hence, the name is LU decomposition. No? The original matrix A is broken down into two sets of matrices in the form of a lower and upper triangular matrix. So several steps are involved to demonstrate this, no? But here we can prove that if we want to solve a set of linear equations, so we have the coefficient matrix A. We want to solve the value of x. This is some column matrix, no? So when we want to solve the values of the unknowns, no, in this column matrix, we have the constants at the right side of the equation being grouped together through another set of column matrix at this side. No? Now, if we break down the original matrix A into components L and U, which is again of a lower triangular matrix and an upper triangular matrix, then we have the following equation. Then we multiply both sides of the equation by the inverse of the lower triangular matrix, no? So this is not done in the actual operation, but this, just to demonstrate what what happens. So if we multiply both sides of the equation by the inverse of the matrix L, then this side becomes an identity matrix, no? And then the upper triangular matrix is kept on the left side of the equation. Now we want to solve for the inverse of the matrix L at this side. So let's consider the following. No, if the inverse of the matrix L times the constant is equal to some intermediate set of values, no, called the matrix Z, then the product of the original matrix L and that intermediate matrix Z. So this is a set of values as well, no? Which corresponds to a column matrix. And this can be equated to the original uh, column matrix where we have the constants at the right side of the equation. And so, using this, then we can equate the upper triangular matrix and the x column, which are the set of variables we want to solve, into now the, yan, so we substitute this guy right here with the matrix Z or zeta. Now we won't be doing this, but we can skip, or when we perform the decomposition process, we skip to this two sets of equation, and then we can be able to find the solutions or the values of x using the two operations here. Okay, so solving for systems of linear equations, if we have the original matrix A, and then a set of variables or values you want to solve for a given constants, no, at the right side of our equation, group as a column matrix, then we can decompose the original matrix A into a lower triangular and upper triangular component. Now, solving for the lower triangular matrix and the intermediate values zeta or z using the column matrix C, we can obtain these z values. No? And then once we have the z values, we apply this column matrix here into this equation u of x to solve naman for the values of x. Okay, so how will it be beneficial for us to learn this approach? Now, if we consider the computational efficiency in terms of the time it takes for the process of calculating matrices using both the Gaussian elimination and the LU decomposition. So here are the number of steps required now. For the forward elimination, the calculation time is given by the following, where the n here is the size of the matrix. No, if we have n number of unknowns and n number of equations, then using that n value, we can solve for the calculation time, or at least the number of calculations involved, no, in the Gaussian elimination. So this is being broken down into the forward elimination process and the back substitution process. For the LU decomposition, this involves three sub steps. The first one is the decomposition to LU, and then the forward substitution is given by this equation, and then the back substitution is given by this equation. Now, in solving for systems of linear equations, the total time it takes for both cases are similar, no? When solving for the systems of linear equations. However, yeah, so the LU decomposition proves its worth when it comes to finding the inverse of matrices, because as you can see, in both cases, no, uh, solving for the inverse of the matrix involves exponential function. So the time it takes to solve the matrix is an exponential function of its dimension. So it may be very easy to solve for the 2 by 2 matrix, rather more tedious to solve for the 3 by 3. But I don't know if you guys have tried solving for 7 by 7 matrices. Have you done it before in your prior courses? Can I see a show of hands if you were able to solve for matrices of that dimension before? 7 by 7 or even higher? Has anyone tried to solve matrices of such dimensions before? I think in some cases you've encountered 5 by 5, but I don't know if you've tried 7 by 7 or 8 by 8 matrices. Have you encountered such uh, problems before? Not yet, no. In some competitions, I think there have been some cases, no, where such problems are presented 7 by 7. Now, I don't know if you've encountered AI concepts before, but most of the algorithms or much of the algorithms in AI and data science are a bunch of linear algebra operations, essentially matrices, no? Image processing, for example, filters, for example. No? If we apply filters in an image, we consider an image actually, no? Of course, you're familiar with the dimensions of typical images. High definition for video clips, no? Actually, video clips is a set of images being constantly rolled or running images, no? Running set of images. So if you're dealing with high definition, then the dimensions, at 720 or 1080 and so on. Yan. So when processing images, we treat images as a really huge matrix, and then filtering is applying a smaller set of matrices, let's say 3 by 3 or 4 by 4. Usually 3 by 3 works just as fine, to perform calculations on the values of individual pixels. So if you're working with 720 matrix or 720 image, then you have a matrix of 720 uh, dimension. Well, it's not a square matrix. No? The images are uh, rectangular, but the kernels or the filters being used are usually square matrices. So imagine if you're solving or working with matrices of higher order or higher dimensions. So the difference is obvious here, no? So if you're working with 2 by 2 or 3 by 3, it may not be immediately appreciated. But imagine working with matrices of higher dimensions, no? 10 by 10 matrices, 100 by hundreds, 100 equations, 100 unknowns. Yun. So for data science, that's not something new, no? Dealing with the huge data sets. And that's when you can start to appreciate, no, that the process of LU decomposition provides a much more efficient routes or options for calculating systems of linear equations. Yeah, so we can see na for higher dimensions like n at 10,000, so the calculation time when comparing the naive Gaussian elimination versus that of the LU decomposition is 2,500. No? So when dealing with higher order or higher dimensions, then it will be more efficient to uh, use or consider the Elliott decomposition approach. Okay, so before that, let's do some exercise. If you can still recall, no, our topic from last time. So I'll just try to switch my screen. And so, can you guys try to work on this problem? So please solve for the following system of linear equations: values of x sub 1, 2, and 3. Let's try if we can work this in 10 minutes. Sige, I'll wait for your answers in the chat box. I'll try to give you around 10 minutes to if you can be able to solve this system or the solutions for this set of equations. Okay. So I'll wait for your answers in the chat box. If you have questions, you can post your questions or concerns in the chat box as well. Okay. Any other answers so far? Okay, and any other answers so far? Okay, no. So we will check later if your answers are correct. No. So let's go back to our discussion on the LU decomposition. So again, as the name implies, the technique requires us to break down the original matrix A, which we are solving for, into two set of matrices, no, which are in the form of a lower triangular and an upper triangular matrix. Now, the upper triangular matrix U is the same as the coefficient matrix at the end of the forward elimination step. So we will just cut it here, and then we have the U matrix. Now, the thing is, the lower triangular matrix can just be obtained by using the multipliers that we've used in the forward elimination process. And then, by default, this method requires us to have the one coefficients in our diagonal. Right. So using the Gaussian elimination that we have discussed last lecture session, no? We are able to reduce the row 2 and eliminate the leading coefficient for the second equation, no? By using these coefficients. So we divide this coefficient 64 by 25. Then we have the multiplier 2.56. So we use the values of row 2 and then subtract row 1 times that multiplier, and then we are able to eliminate the leading coefficient for row 2. Repeating a similar step for row 3, we divide 144 by 25, and so we have the multiplier 5.76. And we use the value of row 3 minus row 1 times the multiplier 5.76, and so we are also able to eliminate the leading coefficient for row 3. Now we kind of do similar process between rows 2 and 3 to eliminate this guy right here. No? So we divide 16.8 by 4.8, or the negative values, and then we obtain this multiplier right here, and then we use row 3 minus row 2 times the multiplier, and then we are able to eliminate this guy right here. And so we have here the upper triangular matrix. Now, the thing is, the lower triangular matrix is just obtained by the multipliers that we've used, no, in the forward elimination process. So the 2.56 here will be used here, 5.76 will be used here, and then the last multiplier 3.5 to eliminate row 3 will be used here instead. No? Okay. Just to check, if you guys are still up there. So what does the result, no? If we multiply the matrix L and matrix U, what are we gonna obtain if we multiply L and U? Are you guys still there? So question is, what will be the result if we multiply matrix L and matrix U? Anyone? Then what happens if we multiply matrix L and matrix U? All right, thank you again, Mr. Carinogan. So, yan, so we go back to the original matrix A. No? So that's the point. No? So if we multiply L and U, we go back to the original matrix A as defined or as described by the properties of L and U. Now, so let's try to solve the systems of linear equations using LU decomposition. So we have the upper triangular matrix here and the lower triangular matrix, and this will involve the first steps of solving the column matrix Z right here. No, so just like in the process of back substitution, no, where we start with the row or the equation where we have only one unknown. Here in this case, we start with the first row or first equation. Then we can immediately obtain the value of Z1, which is 106.8. No, we can immediately see here now that this is the value of Z1. So this is a typo here. So this should be 106.8. Just take note of this, and then we can immediately use the value of Z1 to obtain the value of Z2 in the second row, second equation right here. Now, once we have the Z1 and Z2 from here, then we can use this value to solve for the value of Z3 from row 3, equation 3. Yan, so obtaining the values for Z1, this is already 106.8 as described in the column matrix. We plug in the value of 106.8 into the second equation. We have Z2 as negative 96.2. And then we plug in the values of Z1 and Z2 into the third row, third equation. So we have 106.8 here and negative 96.21 here. So we have Z3 at 0.735. Still, this is not the solution. So this is an intermediate uh, value or set of matrix for obtaining the actual solution X right here. No? So what happens next is that we will equate the upper triangular matrix into the uh, intermediate values here using the variables we are solving for. Now in this case, this is again very much the same as the box substitution process. We start by working the bottom section or row 3 where we only have one unknown. So transforming this into the three sets of equation, we have the following. So we begin with A3 right here. No? So A3 is obtained by just dividing 0.735 and zero point 0.7. So we have A3 right here. And then using the value of A3 for the second equation or second row, we can solve for the A2 value here at 19.7. So once we have the A3 here and then the A2 here, we use those values for first row, first equation, and then we have the following for A1, no, which is 2.9. So this is already the solutions that we've obtained using the Elio decomposition. So is that somewhat similar to the ones you've obtained from the naive Gaussian elimination? So it's kind of the same thing, no? So I guess we can all agree that using this approach, we can solve for systems of linear equations. So is this clear for everyone? Are the steps clear for everyone? Okay, can I see a show of hands if everything is clear up to this point? All right, thank you guys. Okay, so but earlier now we've seen in the previous slides now that in terms of computational efficiency when solving for systems of linear equation, that this is just as efficient as the Gaussian or the naive Gaussian process. So we will demonstrate the value of how useful the method of Elliott decomposition is when we try to solve for the inverse of the matrix. So first, uh, let's define let's provide the definition first of the inverse of the matrix. So how would you define, anyone? Any volunteers? How would you define the inverse of a square matrix? Again, if you're having issues with your audio systems, you can use your chat box, no, to comment or raise questions if you have concerns to clarify, right? So my question is based on this equation. How would you define, or what is the definition of the inverse of a matrix? Okay, so here we define the inverse of a matrix, uh, denoted here as B, as a matrix where if we multiply such matrix with the original matrix A, the result is that of an identity matrix. No? Okay, so can you guys recall how to solve, or what the steps involved in solving for the inverse of a matrix? Can you share what you can recall about the procedures for solving the inverse of a matrix? All right, that's right. No, thank you again, Mr. Karinogan. So you have to determine the adjoint or the adjugate of a matrix and divide it by the determinant. So each of which are involves several steps. No, the adjoint or the adjugate itself has some various steps, and of course the determinant is equally tedious, no? So again, imagine if you're working on higher dimensions, then this will take a lot of time. But here we will demonstrate that using the LU decomposition method, we can be able to solve for the inverse of a square matrix. No? First is that we define or we make use of this equation, no? So that the product of the original matrix A in the first column of the matrix B, which is your inverse, no, should be equal to the following. Yan. So this is the first column of the identity matrix, right? And the first column of an identity matrix has a 1 here, followed by several zeros, which is if you have an n by n matrix, then this will be n minus 1 number of zeros. And then what? Then we will just repeat the same thing for each columns. For the second column, we multiply the original matrix A, and then the second column of the inverse matrix B. So the result will be the second column of the identity matrix. So very convenient, right? Because we know that the second column is 0 and then 1 and then followed by several zeros. And then we repeat the process for the third column and so on and so forth. So conveniently, no, we can work on each columns by performing the same steps that we've done earlier, no? Like when we tried to solve for the solutions of SLEs. So let's try to work on the same problem, no? Because we've already provided the decomposition procedure, and we were able to obtain already the L matrix and U matrix previously in the same matrix, no? To solve for each column B requires 2 steps. So we have to equate the lower triangular matrix to the column matrix, which are a set of constants, and then we obtain the intermediate value Z right here. So once we have the Z value here, then we can solve for the unknowns or the X here using the upper triangular matrix. So starting with the column 1, no? So we have the column 1 of the identity matrix as 1, 0, 0. So in this example, we have 3 by 3. So fairly convenient demonstration. For the intermediate values Z1, Z2, and Z3, we have this column matrix. And then working, beginning with the row 1, we immediately have the Z1 as 1. So you can see that this is a very convenient approach in a sense that for any other problem, we begin with this value Z1 is equal to 1, right? And that is regardless of the dimensions. Z2 will also have a coefficient of 1 when working with the second equation, and then similarly Z3 will have a coefficient of 1. So those are the features of this technique that makes this convenient for us to work on the algebra part. Right? So Z1 is equal to 1. We plug in this value into the second row, second equation, and so we have the Z2 value at 2.56. Now once we have Z1, which is always 1, and Z2 at negative 2.56, we plug in those values into the third equation, then we have Z3 at 3.2. Okay, so we have the Z matrix for column 1 right here, and then we use the upper triangular matrix, no, here, and this is the Z matrix for column 1. All right, and then what's next is that we can now solve for the column 1 of the inverse matrix. So in this case, this will be again similar to back substitution process, in a sense that we're beginning with the row 3, having only one unknown in this equation. No? So we just substitute, or we just divide 3.2 by 0.7, and then we can obtain the B31. And then once we have the B31, we use this, plug it into the second row equation here, and then we have B21 at negative 0.95. No? So using B21 and then the B31 originally here, we plug it into the third equation, and then we can be able to solve for B11 at 0.04762. So now we have the first column of the inverse of A, which is the following. So you can just imagine that we repeat the process for each two rows, and so we can complete the 3 by 3 inverse of the matrix A. No? Yeah, so these individual steps are omitted here, but you can see now that in the second column we're using 0, 1, 0 for the column matrix here to solve for the second column of the inverse. Similarly, for the third column, we use 0, 0, 3 or 0, 0, 1 rather to solve for the third column of the inverse. And so we can be able to uh, reduce this, no? Or directly obtain the inverse as the following. Okay, so if you can imagine to work on higher order or higher dimensions, 4 by 4 is relatively easy, but it gets more tedious, no? Starting with the 5 by 5, and now you can start working on 6 by 6 and 7 by 7, and even higher, no? Which is some sort of um, very tedious and kind of unimaginable, no? If you're dealing with the usual approach by solving the adjoint and then of course the determinant for higher order matrices will be a very lengthy step. Okay, so that's all. That will be all now for our discussion today. And so I suppose I haven't yet provided you guys with the, or given you a group activity, no, for the Python programming. Okay, so if you can give me a minute or two, I'll just post the instructions now for your first group project, which involves the earlier topics that we have. All right. So the guidelines for group project one has already been posted in the classwork section. So can they check and can I see a show of hands? No, if you're able to access or if you can if you can now see the guidelines for group project one. All right. Thank you, guys. So just some few points. Okay, so this will be the some projections that I have for uh, the succeeding weeks, but maybe we will go ahead with the integration process here now, so as to give you more time because the second group project will be based on the numerical integration. So maybe next week now we will have this set of topics for numerical integration. And then again, please be reminded, no, that your group project will be presented. So, submission dates for the final paper will be ahead of this week 15. No? So I'm thinking of week 14. So by around week 14, then you should. The expectation is that you're done with the documentation and all related deliverables, so that the project presentation will be at or around week 15. And so just like to share some few points for the group project one. No? So group project one requires you guys to create a program to perform route location or using open and close route finding methods. So it will allow the user to choose one of the methods and input guess for interval points if applicable. And the program will calculate the approximate value of the root along with the percent relative error. So the calculations will stop when the absolute value of the error or relative error falls below the uh, criteria, which is at 0.05%, or if it exceeds or reach 20 iterations. So you have to tabulate the results. It has to be correct with to at least three significant figures. Now the presentation will serve as your practice, no, to perform or to to create documentations using the Tripoli format. Right. So you can, yeah, so you can see, no, that your group report will be presented in a conference paper form, no. So the it will be divided in some sections. At least the basic parts uh, consist of the following. No, you have to present some introduction, cite some concepts from books or other reference, no? And then the objectives of your paper, some flow charts and pseudocodes if applicable, and then you have the simulation data and results. So you can take a screenshot of the display. So that's one way of presenting your outputs. And then your conclusions and the recommendations for all parts. If you're citing concepts from other sources, then you have to perform your citations using the IEEE format. And of course, your references. So I provided the link for you to check the template, so you can download the template. So the template will be downloaded immediately after you or once you click the link. Now I'm gonna give you guys some idea on how um, citations are created, no, using triple E. All right, so let's say you'll be referring to this article, no? And so one way some references can be cited using this link. So let's say you have references, or you use as references some articles from Explore. Then you can just copy this one because this is already formatted using the Tripoli citation format. So this is different from APA or MLA. If you guys are, I suppose you're much more familiar with APA, no? Tripoli is actually something like a modified Chicago format, but it has its own modifications. So in this case, you don't need to use the keywords here. You can just if you copy this, even the keywords will be included, no? So you only have to highlight until the DOI part, no? If you're citing journal papers or similar references. Now, yeah, so that works as a citation. Another way is to use the DOI, no? Or this is similar to ISBN if you're citing some books. So you just have to copy the DOI, which is the direct object identifier. So again, this is somewhat similar to ISBN for books, but this is generally being the indexing tool for research papers and journals, including conference papers. Switch my screen to an online tool called the citation generator. So this is by citation machine. Just do a Google search of IEEE citation generator, and this is one of the options that uh, Google search will give to you. So here, as you can see, this is a free version. Of course, there is a paid version, but definitely you're not required to do so. No? So you can use websites as sources, books. For websites, you'll just paste the URL, of course. For books, then the ISBN is typically being required here. Now, for journals, conferences, and other publications, as I've mentioned, we have the direct object identifier or DOI. So you place the DOI here, no? And DOI.org, and then a bunch of numbers follows. And then do a quick search. Yeah, so here's the title that we've seen earlier. No? It has been able to pinpoint the specific literature based on the DOI. So we click cite, and then just proceed with the other steps, right? And so you can see here the details, no, the authors list are provided here. Date of publication is also given. So we will just proceed with the last option, which is to complete the citation. And then you have here, no, the reference. So you just copy the citation. Okay. If it's your first time to load this page, then you will be prompted to play an ad, which runs around 30 seconds, no? Because of course you're using the free version. So like any other online platforms, you're required to view some ads for you to use this uh, platform for free. Okay, and then once you click that, the citation is already in your clipboard now. Okay, so as I mentioned earlier, the link for the template is already provided in the um so the link for the template is also provided in the instructions, no, or in the guidelines that I posted. So you just click that and template A4 template will be downloaded. So this is the template. If you read through the explanations or the narratives here, these are actually the guidelines, no? They provided the guidelines in this exact template. So if you read that, the comments here, then you can get some insights on how to properly structure paper. Okay, so let's begin with the title now. So whatever your title here is, just you're just gonna have to replace this one, then delete everything. So these are for subtitles. In most cases, you won't be needing this, so you can just delete the same. Now, the default setting is allows us to use three authors names here now. So let's try to work on the first one. So you just type your name here. The more appropriate to include your middle initial, no? And then the name of the organization. So this should be italicized. That's for the second line. And then the organization, no? And then the city in the country should be the city. This refers to the organization, no? Not your personal residence. And then your email, no? Yun. So that's the default format. If you check some online sources, then there are ways as well to present papers where for similar affiliations, then all the names are being presented in a single column, no? It's a convenient one, but it requires you to do some adjustments on the template itself. No? So let me just for similar example. No? Yeah, so this is one way of presenting your authors list as a single line if you have shared affiliations. So you just have to make some adjustments and then list all the names in a single column here. So in many cases, that will be more convenient than the separated or the separate list. No? So it's up to you on how to make your paper presentation more pleasing or more appealing. No? So let me just go back to the template. So the abstract here is should be around less than 200 words is okay, no? Uh, Good measure, you can work with between 150 words to 200 words. So this is just a very short introduction to give your readers the idea of what to expect from the rest of the paper, right? So you have your introduction here, then your sort of methodology for the section 2. No? So I'd like to go straight into the reference section, no? Because that's what we've been discussing earlier. So here are some example format. Again, this is different from the API format that you guys are we're all very much familiar with. So just paste, I suppose we still have in the clipboard the previous citation that we've generated. And as you can see, no, that the same numbering is already generated by the citation generator. So you just have to delete that, no, because the template already provides the numbering. Now, after the reference section here in this template, there are various comments that we have to delete some of this, you know. But if you can look at the explanation, it says that the template will number citations consecutively within brackets. No? So the proper order of citations here in the reference section should be the same way as should be the same logical order in which the references were mentioned in the paper. So if you've mentioned some reference in this section, let's say here, no, and then your reference is you have the first reference here. So you put the bracketed number one here, and the second should be number two, and so on. No, it should not be chaotic. It should be logically presented that the first reference mentioned in the entire document is the number one, then the next will be number two, and then the number three. There are other comments here that you can remove. Yeah, so this is for funding agencies wherein some researchers, as you know, are funded by different organizations. But anyway, since we're just practicing uh, paper writing here now, so just remove all the other parts which are unnecessary. So if you're presenting equations, there is also a format for that as presented in the template. No, it should be numbered like this one, and then if you are If you'll be citing or referring to an equation provided in the document, then you can use. So you just have to follow the comments here when presenting equation. And then some bullet points are also applicable. And again, tables. No? So the tables have to follow this template here. It might be tricky for most cases to insert another column. No? So you just have to uh, find way around if you need more columns. And then you have to make some adjustments. So the rule here is to see to it that the tables fit inside the margins. You cannot adjust the margins because these are essential part of the template. And margins, the default margins should be followed at all times when dealing with the triple E format. Adding rows is a convenient process, no? So only the columns are kind of tricky stuff. So some other areas that you can remove are the acknowledgement section here that will be that won't be necessary, no? So you can just get rid of that, as well as the box here, no? So these are just additional comments. Now here there are additional comments here that if you try to delete this, and it destroys the formatting, no? It turns to a single column, which is not consistent with the triple E conference paper format. So you have to be careful when editing some parts of the document, especially the end part, no, or the end section, so as to retain the two column presentation consistently. And again, in the reference section, these are additional comments that you can get rid of. It just provides you the guide, no? So, but this has to be deleted. Right. So the reference section should look like this one, and then all the other references will be added here later, and all the default references provided by the template have to be deleted. Okay, so I hope I was able to impart with you some something useful, no? At least the expectation is that in your final project requirement, the same approach to documentation has to be followed. So group project one will be a good exercise for you, know, to practice documenting or doing your documentation using the triple E format. Then of course you can check for other studies or other references online to check if you are complying with the documentation structure. No, there are also video clips from YouTube and other sources where some guidelines are discussed, no, on how to properly structure, format, and logically present your paper using the IEEE conference guidelines, no? And of course the references and the in-text citations and all related stuff. Right, so I guess that's it for me for this week. Are there any questions, concerns, or clarifications so far? Okay, so if none, can I see a show of hands if everything is clear up to this point? Okay, so so if there will be questions, you can just feel free to send me a message, especially for the project yung group project related matters, no? If you want to give me updates, it will be very good idea for you to give me updates or heads up on your progress. If you have questions, then you can just respond or reply in the previous email thread that we have. No? So each group has their own email thread. You can use that to so that all the project related matters are being consolidated in a single email loop. Right? And that's it for me this week. And see you guys next week, no, for the integration topics. And have a great week ahead. And see you guys next week. All right. So I'm gonna end the session now. So thank you guys and stay safe.
Thank you po, sir.
Thank you po.